Okay, so hello everyone, and thank you for joining today's TVS Science Colloquium. I would like to give a very warm welcome to our speakers today, Martine, Lokken, and Alex Gagliano, who will talk about simulating host galaxies for transients in the second PLAsTiCC challenge. So as usual, the talk will last about 30 to 35 minutes, which leaves us plenty of time for questions. And the speakers today told me that they would very much appreciate any feedback our group would like to give. So feel free to give any feedback after the talk. I would also like to point out that the meeting is being recorded and will be uploaded to the TVS YouTube channel later. But before we begin, I would like to quickly introduce our speakers. Martine Lokken is a third-year PhD candidate at the University of Toronto, where she works with advisors René Hlodžek and Dick Bond. Her thesis research focuses on studying cosmic filaments to better characterize large-scale structures and test cosmological models. More broadly, she's interested in developing and making use of simulations to test cosmology theory and support observations. It was through this interest that she began working with the Rubin Dark Energy Science Collaboration on this project to correlate simulated transients with host galaxies for the second PLAsTiCC challenge. And Alex is a third-year NSF graduate fellow at the University of Illinois at Urbana-Champaign. He studies the statistical and event-specific correlations between supernovae and their environments with Dr. Gautam Narayan. He's interested in using these relationships to better characterize the progenitor physics of explosive transients, particularly for rare events. With the Rubin Dark Energy Science Collaboration, he developed software for host galaxy association, photometric classification, and transient simulation for PLAsTiCC challenge. So this is also what our speakers will talk about today, and the floor is all yours.
Great, thanks very much, Katya. Let me share my screen. Okay, hopefully you can all see this okay. So as Katya mentioned, I'm Alex Gagliano. I'm a grad student at the University of Illinois.
And I'm Martine. I'm a grad student at University of Toronto.
And today we're going to be talking about a project that we're completing on behalf of the Desk Alerts topical team to simulate the properties of host galaxies for different transients for the second iteration of the PLAsTiCC challenge. So before we jump into why we might want to do this, we should talk about what the PLAsTiCC challenge is. PLAsTiCC is an acronym, albeit a somewhat forced one. Let's see if I can get this right. I believe it's the Photometric LSST Astronomical Time Series Classification Challenge. So version 1 of the challenge took place end of 2018 through early 2019. And the main objective was to kickstart machine learning efforts for photometric classification of transients in LSST-like datasets. So for the challenge, there was a massive infrastructure put in place for simulating transient events. In total, there were about 3 million U-Grizzy light curves simulated that were similar to Rubin Observatory photometry. And the breakdown of the test set is shown at left here. You can see, unsurprisingly, we have predominantly type 1a supernovae, but there are lots of other transient classes in here too. And by and large, in terms of the primary objective of photometric classification, the version 1 challenge was a success. And the dataset from version 1 is still being used today. So here's an example on the right of a variational autoencoder used to detect anomalous transients using the PLAsTiCC version 1 dataset for training and validation. So this is really exciting.
And PLAsTiCC version 2 is going to be launched in September, this upcoming September. And so we're rapidly preparing for this launch. And the purpose of PLAsTiCC version 2 is going to be to evaluate the real-time broker performance on a realistic LSST alert stream. So the brokers are these teams that are going to be working on storing and processing and classifying the alerts, and also informing the follow-up that will be planned by various smaller observatories on interesting events. So there's various teams, and they're going to be tested by various metrics on how well they can perform these tasks. potentially, in addition, they may collect active source features and maintain source databases. And the way they're going to be tested is through this alert stream, and then in terms of how well they do various metrics in processing that alert stream. The alert stream is a set of LSST-like alert packets that has to preserve environmental correlations with, for example, with host galaxies. And it should contain a representative sample of the events that we expect from the long-running LSST observations. And so this is overall going to be an iterative process where we send alert packets to the brokers, and they run their pipelines that they've prepared on these alert packets, and then they can send them back to the people who have simulated the alert stream and possibly do updates. And overall, the goal is then to have good compatibility between the alert stream and the brokers to prepare for the actual observations taken by Ruben.
So there are a couple of ways in which the version 1 dataset was unrealistic. So it was not characteristic of the data that broker teams are actually going to receive from LSST. So number one, full phase light curves of each transient events were provided to the classification teams. And this is valuable for kind of the first step of machine learning photometric classification, but for rapidly evolving transients, you're not going to get the full phase light curve. And if you wait for the full phase light curve, you're going to probably miss the event in follow-up. And there's also a lot of early science that goes on with different transient classes that would benefit from real-time photometric classification, such as would be possible given just individual sets of alerts, as you're actually going to get with the LSST survey. In addition, there were no postage stamps provided to the classification teams. So if I'm an astronomer looking at a data set and I get a trigger from LSST and I want to know whether this is a real transient or just some bogus, maybe a cosmic ray or something like that, the first thing that I'm going to do is look at the postage stamp, see whether it's associated with potentially a big bright galaxy, and this can lend credence to whether it's a real event. So we're working on incorporating postage stamps into our alerts as well for V2. And in addition, there was no host galaxy information provided to different classification teams. And we now know that host galaxy information, both at the local and at the global level is valuable for classification and for teasing out different progenitor physics. So this plot kind of center here is from a paper earlier this year that I worked on. This is a principal component space of host galaxy properties of 3 different transient classes. You can see that you can already begin to distinguish between the transient classes solely based on the photometric properties of their host galaxies. And here are a few postage stamps of different locations in this space. And then all the way to the right, Alersi is a transient broker team that has developed a photometric classifier using a neural net trained on the first science images of an event, which includes host galaxy information. So it's a postage stamp of the field. And based on that, you can get probabilities of a class being, for example, in the top plot, a supernova, or in the bottom plot, more likely an asteroid. And so all of these science results are dependent upon host galaxy information.
And to further the case for including host galaxy information in PLAsTiCC V2, there have been various studies done, including the one that Alex did, that show that there's these correlations between the transient type and also various properties of the transient and the host. And so the goal of including realistic host information that replicates the existing data that we actually have from observations, but in simulations, is that then the alert brokers can learn to start incorporating host information into their classification and hopefully use that to improve their classification. So some of the properties that are expected to correlate with the transient class are some observed properties like the brightness, color, and shape, intrinsic things like the star formation rate and the mass of the galaxy, and also the transient location within the host. And in particular about that last point, there were a couple of studies done that showed that there's quite a correlation between gamma ray bursts versus core collapse supernova and their environment, both in terms of the properties of the host galaxy as a whole, and also in terms of the localization within the host galaxy. What kind of properties did the environment around them have in that galaxy? And so something like the distance between the transient and the host nucleus may be important to include as an additional part of the classification. And because of that, in version 2, we are now including realistic host galaxies. And that's what Alex and I have been working on. So things that we're including in version 2 are realistic transient abundances for galaxies of different properties, correlation between the properties of the transient itself with the galaxy properties, for example, brighter transient going off in a more massive galaxy. And in addition, we're going to include hostless transients. So this could be because of observational reasons in the real LSST observations. So for example, if LSST observes a high redshift supernova that's near the magnitude limit, then Rubin may only see the supernova itself and not the host galaxy. And so that transient may appear hostless. There could be an actual intrinsic effect where if a supernova goes off quite far away from any host, which we actually see sometimes in the real data, that's going to appear as having no host. And also algorithmic, if the algorithm that's finding associations fails and just does not end up associating a certain host. And so we're going to include some of these hostless transients in the simulated catalog. In addition, we are including this position with respect to the host galaxy nucleus and posterior PDFs for photometric redshifts.
So in addition to the host galaxy properties that we're working on incorporating into our version 2 dataset, there are also new and updated transient models. And here are just a couple of examples, not an exhaustive list by any means, but there are in particular variable star models that have been incorporated Delta Scuti, Cepheids, and dwarf novae that a postdoc and an undergrad in my group are working on now simulating using this SNANA code that we'll talk about a little bit later. And in addition, there have been some models that have been updated based on theoretical work. So type 1b and 1c supernovae, M dwarfs, Vedshaw is also an undergrad working on this, which is very impressive. And the kilonova model has also been updated both on the observational side, so what type of photometry we would expect to see based on the 1 kilonova that we've detected, but also on simulating the LIGO alerts that we would expect from that particular kilonova. So you see bottom right, a kind of sky localization from a simulated LIGO alert from a kilonova event.
So that's a lot of information. And this slide also has a lot of information, but hopefully it can give you more of a sense of how exactly all of these pieces are going to fit together. So on our side, we're starting by pre-processing the GHOST data, which, as Alex mentioned, is this large catalog of around 16,000 supernovae and host galaxies that he pulled from Pan-STARRS data. And it does represent a very large sample of many different transient classes and sort of the best available data that we have right now. However, because of observational limitations, it's very skewed towards low redshift and bright galaxies. And so we are using the GHOST data to then make a much larger and more high redshift sample of host galaxies from Cosmo DC2, which is the synthetic sky catalog that was created for the use by the desk. After we have our host galaxies from Cosmo DC2, we run this through the simulation phase, which is the middle part here. So we use this code called SNANA to simulate transients and their correlated hosts. And then with the outputs from SNANA, we will create an alert stream. And this alert stream is what will go towards the brokers so that they can start testing their classification pipelines. In addition, what Alex had just mentioned with the LIGO localized event sky maps, that information will also go towards the brokers so that they can learn to figure out if you expect a certain LIGO event to correlate with an analysis T event, and then follow up on that, it might be a kilonova. So ultimately, all of this is flowing towards the brokers so that they can test their pipelines and then iterate back with us.
So we'll talk a little bit about how we pre-process our data in a bit more detail than Martine just went over on the kind of the left side of that flow chart, and preparing our data set with the correlations that we want for different classes of supernovae for simulating with SNANA. So as Martine said, we start off with the GHOST database. This is Galaxies hosting supernovae and other transients, although right now it's just supernovae, but we had to make the acronym work. So this is 16,000 supernovae and the photometric properties of their host galaxies in pan stars. And there are also some derived properties provided within NED, like the redshift of the galaxy. Second order radial moments are provided by pan stars as well, and that's information that we can use to better correlate the properties of the supernovae with the properties of their galaxy.
Next, we take the GHOST data and match it to Cosmo DC2. But what we do is take a single GHOST galaxy and match it to many Cosmo DC2 galaxies so that we can scale up the sample of simulated hosts that we have and also push to higher redshifts. So the way that we do this is we select redshift independent properties, not fully redshift independent, but at least properties that don't change just because of the redshift. So rest frame absolute magnitudes and rest frame colors, as well as galaxy ellipticity. We take these properties from GHOST and then we normalize them all to scale sort of to the same range. And also we downweight the redshift. We do include redshift, but it's not as important as the other properties because we want to adjust the final sample to be distributed more evenly across redshift than the real observational data that we have, which is very skewed towards low redshift. But we include a slight redshift correlation because these so-called redshift independent properties, of course, do depend on redshift in that there's actual galactic evolution because of cosmic time. So we include those different properties and then we do a k-nearest neighbors matching using scikit-learn, the nearest neighbors algorithm. And in this 60 parameter space, we search for nearest neighbors and we can scale this value of k depending on how large of a final host sample we want. So ultimately what we produce is a simulated sample of Cosmo DC2 galaxies that replicates the distributions in host, but includes galaxies at much higher redshift and many, many more galaxies.
One of the problems that we've run into in matching GHOST galaxies to Cosmo DC2 galaxies is we've discovered that the properties of the Cosmo DC2 galaxies are unrealistically discrete. So here's, for example, G-I color versus redshift, and the Cosmo DC2 galaxies within a certain brightness range are plotted. You see there are these kind of non-physical tracks, especially at higher redshifts. And the reason for this is because there were a limited number of SEDs modeled using this code GALACTICUS, and then those limited number of SED models were propagated through to multiple galaxies. So what you get is multiple galaxies with very similar color star formation rate properties based on their SEDs. And this is discreteness that we did not want to propagate through to our final data set. So one of the unique challenges that this project entailed was trying to find a way to match GHOST to Cosmo DC2 while removing these artifacts. Originally, we attempted using a code IMB-learn to interpolate the properties in this space, kind of smooth it out and generate new galaxies in between these tracks. The problem with doing that is that the IMSIM postage stamps that were generated for all of the Cosmo DC2 galaxies, now you don't have those postage stamps associated with the newly interpolated galaxies. So we've been looking for a way to interpolate the space while still keeping a one-to-one correlation between the original Cosmo DC2 galaxy so that we can use their postage stamps. And the way that we found out to do this was by oversampling just our parameters that are discrete in Cosmo DC2 using normalizing flows. So we've taken advantage of a code called PZ-Flow, a brilliant code written by John Franklin Crenshaw, who's a grad student at the University of Washington, originally using PZ-Flow to develop posterior distributions of redshifts for LSST. But we found that we can train this normalizing flow to learn the global distribution of properties in this space. And then we can sample just those properties again from this space for the same Cosmo DC2 galaxies and update those properties in the catalog. So on the left, you see star formation rate versus redshift. You see all these discrete tracks. Of course, star formation rate is closely correlated with the color of the galaxy. On the right, you have the PZ-Flow sampled properties, the star formation rate as a function of redshift. And so you can see that we still maintain the kind of global distribution of star formation rates in the catalog, but we're able to generate properties that are much smoother across this space. And the good thing about just oversampling these discrete parameters, namely star formation rate and redshift, we don't need to find a way to generate new postage stamps for these galaxies because we still have the original ones from Cosmo DC2.
So finally, once we use the PZ-Flow properties and perform this matching, we can scale up the ghost galaxies to a much larger sample. So these plots are showing that with the original ghost galaxies, the distribution in terms of redshift shown in the upper right. In that blue plot, you can see it's very skewed towards low redshifts as expected for an observational sample. And then you can see a resulting matched sample from Cosmo DC2 on the left here, which is in orange. And we, in this case, have scaled it up by 1,000 times. And this larger sample preserves many of the correlations that are in GHOST, but pushes to higher redshifts. And we can kind of tweak the final redshift distribution of this host galaxy sample by just adjusting how highly weighted redshift is in the matching during the nearest neighbors matching. So this distribution can change a bit to be more equal across redshifts or more skewed towards higher redshifts if we find out that we need that. To validate the matching that I mentioned before, we look at the distribution of various properties. So on the top here is the Cosmo DC2 matched galaxies. So these are all stimulated galaxies, and all of the lower plots are the distributions of the same properties in GHOST. And what I'm showing here is just the closest nearest neighbor, and it's colored by the distance between the GHOST galaxy and the Cosmo DC2 galaxy in that 60 normalized parameter space that I mentioned. So the purple points are worse matches, and the lighter points that are light yellow are the best matches. And you can see, well, with the first pair of plots there, in redshift space, that Cosmo DC2 is the match sample is extending to higher redshifts, but overall similar matching the distribution in I-band magnitude. You can see some remaining issues with the color in the middle plot here, some discreteness that remains, unfortunately, just because it's baked into Cosmo DC2, and we can't do that same PZ-Flow oversampling on all of these properties. So there is some discreteness in the final sample, but again, overall, it matches as well as it can the distribution in GHOST up to the limitations of what already exists in Cosmo DC2. And same for the ellipticity and R-band magnitude on the right-hand side.
So now we have our data set that is pre-processed and a combination of Cosmo DC2 galaxies with the correlations from GHOST. Now we want to feed this into our code SNANA to simulate different transients and validate that our correlations are actually preserved in the events that we simulate. So here is a basic flowchart of how we do that. We input information based on the host galaxy and the transient properties. So this is, for example, the class of the transient. In the case of type 1a supernovae, we also include correlations with SALT2 fits. So SALT2 is the model for type 1a supernovae. Properties of the SALT2 fits seem to be correlated with different properties of the host galaxy in ways that I'll talk about in the next slides. We then generate the light curves of supernovae or other transients based on redshift-dependent rate models from the literature. And for each supernova at a given redshift, we pick some margin in redshift space and we randomly select a host galaxy. I shouldn't say random because that selection is marginalized over the correlations that we've encoded. So if we're more likely to see type 1a supernovae in galaxies of particular properties, then that influences how the host galaxy is going to get selected at this stage. Next, we assign the supernova to a particular location near or within, embedded within the host, and LSST-like observations are taken of that event at each epoch. And the outputs from SNANA are the light curves, the position of the transient and host galaxy, the chosen host galaxy, and the photometric properties. There's also spectroscopy, but that might just be a data product for validation because, of course, spectroscopy is not going to be present for every event within the LSST alert stream. But then all of this data is packaged up into an LSST-like alert and passed in real time to the transient brokers. So here is just a result of a quick run for type 1a supernovae. You can see the sky map of simulated events for type 1a roughly matches what you would expect for the sky coverage for LSST. The redshift range pushes out to a redshift of 1.0. And up top, you have the original GHOST database. And on the bottom, you have the transients and associated host galaxies that were simulated with SNANA from our matched catalog. So you can see that this distribution already pushes out to higher redshift and also starts to curtail around redshift of 0.8 due to the limitations of the survey. So we've just now simulated type 1a and type 2 events, but of course, our primary objective is to simulate all of the transients from the version 1 dataset, as well as the new models that have been incorporated. For type 1a supernovae, the rate is correlated with different properties of the host galaxy and with the photometric properties of the event itself. So this is based on a series of earlier papers by Minucci and Sullivan that found they modeled their type 1a event rate as being a function of some mass and star formation rate up top, multiplied by a SALT2 stretch and mass function on the bottom. So this basically tells us on the top that you would expect type 1a supernovae to happen more often in highly star forming and large galaxies, more massive galaxies. And then there's also a correlation with stretch and the mass of the host galaxy that we're going to see in a little bit. So when we simulate those events and we plot these correlations, this is what we get. So this is essentially the visual result of what I had just mentioned, that type 1a supernovae are found in more massive galaxies. There's this mass step that has been investigated in the past of around 10 to the 10 solar masses. But if you're star forming enough as a galaxy, then you can form a type 1a supernova regardless of the size of the galaxy. So this tells us that we're on the right track in simulating these events. These correlations are preserved. I should mention at very low star formation rate, there's an artifact here in this clump of events down below. This is non-visible. This is an artifact that we have removed in subsequent iterations of this pipeline.
And here are some of the early results for type 2 simulations. And I'll also show the equations for type 1BC. So they're modeled similarly in terms of their rates. So For passive galaxies, we just get 0 type 2s and type 1 BCs. But for active galaxies, which is defined by a threshold in specific star formation rate, we have these rate models here where they're correlated with the stellar mass with different exponential dependences. And so you can see in this plot to the right here that there's this cutoff between active and passive at this line of specific star formation rate. And above that, we generally again see slightly skewed distribution towards high stellar mass and high star formation rate. Finally, once, oh, I see a question.
Don't worry, I can take it at the end if you prefer. It's about the masses though. So however you prefer.
We can take it now.
Yeah, so you mentioned 1BCs, but among the 1BCs, Brooklyn type 1Cs are very different in terms of mass hosts. Are you treating them separately or are you packing them with the other stripped envelope supernova?
In this case, we're packaging them all together because that was the model that was done in some previous studies. Alex, I think you are more of an expert in supernova. I don't know if you have any more thoughts on that.
Yeah, I would just say, I think we have to double check whether broadline supernovae are treated as a separate class in the PLAsTiCC data set. I know there's a particular model for type 1b and 1c, but whether broadline has a separate model would then determine whether we treat the host galaxy separately.
Yeah, I think probably not. And it is my recollection that they're treated photometrically because they are, you know, they're modeled from the same MOSFET models, etc.
Right.
But when you look at galaxy properties, and if you want to chat about that separately, we can talk about it. I can give you references. When you look at galaxy properties, Brooklyn type 1Cs with and without GRB, whether they are associated with a GRB or not, they have different metallicity environments.
That would, yeah, we'd love to chat in more detail about that. That would be great.
Thank you. Thank you for taking the question.
Thank you. So once we actually have these simulations done, we have various different methods of then validating that this whole pipeline worked correctly and that we have a similar final result as the expectations from observations. So one of the ways we can do that is by comparing the postage stamps from the GHOST catalog with the simulated postage stamps from DC2. So this is showing an example of that for a single galaxy in GHOST on the left, and that's a postage stamp from Pan-STARRS. And on the right, we've matched that single galaxy to many other simulated galaxies, and we're just showing 5 of them here. And these are the simulated DC2 postage stamps. And you can see that they both appear to be elliptical galaxies, fairly spherical. And we will also check on final results with, for example, color and definitely shape with the final postage stamps.
They also look different because this one on the left, again, is Pan-STARRS, and on the right is simulated LSST depths. And so I mentioned this correlation between SALT to X1 fit for type 1a supernovae. X1 is the stretch. So it's like a scale factor in phase for the photometric properties of an event. And that's found on the right in Smith 2020 to be very weakly correlated with the stellar mass of the host galaxy. So there's an anti-correlation decreasing X1 as you increase in stellar mass. And our plot on the left from the type 1a events we've simulated also shows a weak negative correlation. I should caution that these scales are different. So this one goes down to a stellar mass of around 10 to the 6 solar masses because we're able to simulate smaller and fainter events that you're less likely to actually detect with previous surveys. But having said that, this weak anti-correlation is still present within our dataset. So that's an exciting check that we're taking steps in the right direction.
And finally, as another form of validation, at least for type 1a supernovae, we can make use of the empiricism algorithm, which was created a few years back by Holloin, Marshall, and Beschler. And this algorithm uses machine learning to associate host parameters like color and shape with SALT2 parameters for type 1As. And so I previously worked with empiricists to compare the JLA light curves, so that's from SDSS and SNLS, with empiricism generated light curves for Cosmo DC2 hosts. And so with this, I had looked at more generic broad samples of Cosmo DC2 host galaxies. And the plot here is a comparison between the SOLV2 parameters in red that were simulated versus in black that were from the observational sample. And we'd like to repeat this work, but with the specific sample of host galaxies that we've pulled from Cosmo DC2, so that we can then directly compare the properties of type 1As that we get from empiricism, a totally different algorithm that uses machine learning, with the transient properties that are generated with SNANA, and then after the fact associated to host galaxies based on the input correlations. So those two different algorithms work quite differently, and comparing the final distributions would then be a good sanity check to know that they're both working similarly. So in conclusion, we have a framework in place to generate photometry, spectroscopy, and images of simulated transients and their correlated host galaxies. Right now, we are working through validation of type 1A supernova, specifically the properties of the light curves itself, and validating as well the abundances of different transient types with their host galaxies in terms of the star formation rate and mass, validating with postage stamps, and generally searching for any other types of validation that we can do on this final sample, because there are a lot of steps in this pipeline and a lot of possible sources for error. So we definitely welcome any suggestions on further ways that we could validate our final sample. And in future, we are going to move beyond the transient types we've talked about so far. So far we've done 1As and getting started with type 2s and 1BCs, but we are going to move on to all of the other supernovae in PLAsTiCC, as well as other non-supernova events. So that'll include kilonova, TDs, and variable stars. On the right here are a couple of plots showing some new models for Delta Scuti and Cepheid stars that are going to be input in PLAsTiCC. And so for all of these non-supernova events, we need to search the literature for possible associations between their hosts and those types of transients. So we definitely welcome input on any of that work.
And this final slide is the what can the plastic version 2 dataset do for you slide. So step one, the primary objective of our work right now is in software validation. So the whole effort is in simulating a data set that can then validate the performance of brokers on a realistic LSST alert stream. But it can also be used to validate other analysis pipelines. So if you're developing analysis software for your particular subset of science cases on Rubin data, now you have a realistic simulated LSST alert stream that you can use, including the photometry and the postage stamps provided with those alerts that you can use for validation. And this can also be used to test the impact of different properties of the alert stream on the classification results that you get. So for example, the photometric calibration that we're able to achieve with the survey, we can see how this influences the alert streams that are simulated and downstream the classification accuracies that we're able to achieve for different classes. But most importantly, we're trying to encode correlations for the scientific community. So the brokers will hopefully learn whatever correlations we encode into our version 2 data set during the challenge in September. So the thinking is that these correlations can be used to ensure recovery of particular classes of events, but also if there are events that are found to be strongly correlated with particular properties, and that's something that the brokers get really good at training on, then we can use it to inform the LSST data products team that this is a simple derived metric that could be really valuable to include in the alert stream once the survey comes online. So this is the type of kind of feedback that we can incorporate into our project. So the question that we wanted to just open up to the floor is, what kind of correlations are you all interested in preserving or looking for in the LSST alert stream, and how can we better enable your particular science cases? And so with that, we'll end it there and say thank you very much.
Okay, thank you both. So we have a lot of time for questions and feedback. So any questions already? Yes, Alessandra, please.
Hi, so first of all, I wanted to say this is an impressive work. Thanks a lot for the presentation. It was very nice. Then I have a couple of curiosities mostly. First one, you mentioned eventually when you got to the kilonova stage simulation, potentially incorporating correlations or links with LIGO alerts. So I was wondering if you could elaborate a little bit more on what you have in mind. And then the second thing I was curious about, is probably too early, but would there be a way at some point that you could make part of your matrix results from observations, photometric observations, or light curve observations at other wavelengths, to then go and train your classifier somehow?
So I can definitely answer the first one regarding the LIGO alert stream. So Deep Chatterjee is a postdoc at UIUC here, and he's working on improving both the theoretical kilonova model, so what kind of photometry we would expect from it, but then also the simulated LIGO alert stream. So the thinking would be that even though the main objective here is to test alert brokers on LSST alert streams, we'll have separate LIGO triggers that can be simulated and fed to the brokers. And if a broker is advanced enough to be able to ingest both the LSST alerts and the LIGO alerts, then they can do some cross-correlation studies. And if they find spatial coincidence of the alerts from various places, then this can better inform the type of follow-up that we might want to do on that event. So this is not the main objective of the Plastic version 2 challenge, but because now we're having realistic LIGO triggers simulated, we're hoping to incorporate this and to just see what kind of science we can do from it.
And if I remember correctly, the second question was about the metrics that will actually be used to assess the classifiers. So as far as I know, this is still very much in progress. I don't think there's been very much decided yet on which metrics are going to be used. So I think this is a place where if you have suggestions for which metrics you think would be important to include, I definitely recommend getting in contact with the folks who are in charge of that, who I believe Alex Maltz is one of them. Is that right, Alex?
Mm-hmm.
Yeah, the other Alex. Yeah, are you familiar with the rest of the team that's having the metrics?
Yeah, so two of the Alexes, Alex Maltz and Alex Kim, are both heavily involved in developing the metrics for the comparison of different alert brokers with the version 2 team. But the end result is not going to be, here is like the main broker that has won the challenge and now will be used as the official broker for LSST. I think the more likely case is that the brokers are going to work together and kind of iterate to figure out what properties are most valuable. And so the broker teams, the science teams, and the LSST development teams can all benefit from that knowledge. But if you have knowledge of or ideas for different metrics that could be valuable, yeah, please reach out to the alerts topical team.
Okay, thanks a lot.
Thanks.
Okay, is there is a question from Robert? You're muted, sorry, we can't hear you.
You're still muted.
Sorry, I was muted. Yeah. Well, it's great to see all this effort that's going on in terms of the definition of transients. And I have several questions. First of all, how are the alert brokers defined? Is there a central authority, or can any team that is interested in doing like what you're doing can They simply list themselves as a broker.
Yeah, so technically anybody who is interested in developing a broker team can be involved with the Plastic version 2 challenge. In actuality, the teams with the infrastructure already in place to begin to process alerts is not infinite. There are only a few teams that have seemed to emerge that actually have the frameworks in place to process these alerts. But if there are separate teams that are interested in getting involved that have the people power and the software development capacity.
Well, you listed about 15, I would say, 12 or 15. So, okay, that's approximately the number. I happen to be interested in brighter transients just because I'm a spectroscopist. And so I'm primarily interested in galactic transients. And I assume that there is some, your method is clearly optimized for transients that are in other galaxies. And so there must be some test in determining whether the transient is galactic or in a host galaxy. Well, how do you perform that test?
Great question. Yeah, sorry, go ahead.
Well, I was just going to say, to my knowledge, that in Plastic version 1, there were separate galactic transients and extragalactic ones. So those were definitely distinctly included, but then all jumbled together for the challenge. And I'm not super familiar with how well the teams then did with separating those out. Alex, are you familiar with that?
I'm not familiar with performance on Plastic version 1, but I know, so if I can go back a slide or two. Yeah, I know that the Delta Scuti and the Cepheid models, I'm working with Kostya, this postdoc, to try and determine a way to match those types of transients to either the Milky Way or just nearby galaxies. And that'll most likely look like a different pipeline than the one we've implemented for extragalactic transients, but exactly what that might look like, I don't have a sense.
Okay, well, that was exactly going to be my next question. If I happen to be interested in novae, but to say Delta Scuti stars, I just wonder what the different criteria would be for a delta, a transient like that happens to either be galactic or in a host galaxy. So I gather that other groups are focusing on procedures in which the parameters of the host galaxy, which doesn't exist, are not, not important. In fact, to what extent might your particular procedure be valid for galactic transients? That is, are there important parameters in your classification criteria that do require presence in a host galaxy?
So you're asking about the classification folks?
Yeah.
Yeah, I don't know that either of us are super familiar with what they have planned, because that's going to be what's coming out in the version 2 challenge. I think there were separate galactic and extragalactic transients in Plastic V1, but those would have been, there would have been no host associations. So hopefully the host correlations will be used to help with that distinction. Alex, do you think that?
Yeah, I was just going to say, we should harken back as well to way earlier when we mentioned that we're also trying to make the stream as realistic as possible. And so not giving the broker teams the complete right answer is part of this simulation. So if in actuality, an LSST alert stream will say this is the most likely host galaxy, when in reality, it's an event that happens within our own galaxy, then we want the simulated stream to look like that as well, so that broker teams can be able to distinguish between those events.
Yeah, and after things have been developed further and you're finalized, say, this process to a certain extent, might a package like this be hosted on Astrophy? If you're familiar with Astrophy.
Yeah, so our plan right now is to release the full data set as kind of a data catalog that people can pull from. The architecture that we're pulling together Not sure what the plan is for that.
Yeah, I don't think we have plans to make it part of any kind of Astropy package, because it depends on, you know, the many products that are going in. So Ghost and Cosmo DC2 separately. I think probably some of the other teams would release their work on actual classification. But in terms of creating this catalog, yeah, I think our only plans right now are to host a large catalog of simulated transients and their hosts, which, by the way, we plan to do not only for the LSST observed transients, but also for just a larger data set of sort of everything down to some probably magnitude limit that wouldn't be only limited to what LSST could observe, so that people in the future, if they want to use this catalog for other purposes, for testing different pipelines for possibly different observatories, can also use that.
Okay,
exactly
understood. Well, a very nice presentation, excellent research, and I wish you the best in continuing with it.
Thank you.
Thanks.
Okay, I think Federica has a comment on brokers.
Yeah, I wanted to clarify just so that there are no misunderstandings and wrong expectations. While anybody can build a broker, of course, meaning something that receives alert streams, classifies them, augments them, and classifies them, there is limited bandwidth to serve the brokers in LSST. So there is a selection process where groups that have been working on brokers and are working on brokers have been communicating with Rubin, participating to a number of steps of this process, and there will be a selection of the official broker, which means those will be the engines that will receive the full alert stream, whereas the alert stream may be distributed in limited capacity to other groups that are not the official brokers. And so I'm going to post the link to
and
the
who
page
will
that
make the
describes this
selection
process on the chat. Rubin will, and it's been making the selection throughout a number of steps, including workshops and meetings, and the details of the process are described in the link that I just posted.
Great, okay, thank you.
Sure.
Thanks very much for clarifying that.
I also did have a question, if that's okay, if there are no other hands.
Sure.
So one of the, related to the bandwidth and a few other things, but it is not fully defined what will be the size of the postage stamps that Rubin will deliver to the brokers, and so also what is the time delay between image collection and the delivery of a postage stamp. How much does that impact your the simulations that you're creating?
Yeah, also an awesome question. So we have gone back and forth for a long time about whether we should include postage stamps, what size they should be, and how much information they give the broker teams over just kind of the individual photometric alerts. And I think what we've decided on is that the machinery to rapidly simulate postage stamps is valuable in and of itself. So we are moving forward with simulating postage stamps, and whether or not they'll make it into the alert stream for the actual V2 challenge is up in the air at this point.
Thank you. Excellent answer.
Thanks.
Okay, do we have any more questions? Okay, I have just a very short question. So because we were very involved with Cadence Notes 2 months ago, what is the observing strategy that you're using to simulate the observations?
Yeah, so we're running this both for the wide, fast, deep, and the DDF observing cadences. I believe that's what you're referring to.
Yeah.
So we can run the SNANA algorithm separately for those two. And I believe the plan is to create the alert packets for both of those. Is that right, Alex?
Sorry, say that last part again.
That both wide, fast, deep, and the deep drilling fields are going to be, data from both of those is going to be packaged into alerts. Oh, Gotham also has a comment that the baseline 2018 is the very specific cadence. Yeah, thanks, Gotham.
Okay, do we have any last questions here? I don't see any other hands up. So if we do not have any questions left, I would suggest we wrap it up here. And I would like to thank Martine and Alex again for this very interesting talk. And I will see everyone else, I guess, in 2 weeks for the next colloquium that we have. Thank you again, and bye.
Thanks, everyone.